The Rohde&Schwarz SFI 100A wideband IF vector signal generator has been developed to meet the bandwidth needs for demanding applications such as early 6G research, millimeter wave WLAN, high-capacity wireless backhaul, sensing, and automotive radar. In this video, I show how the SFI 100A simplifies modulated measurements at IF and in the sub-terahertz region in combination with the Rohde&Schwarz FE front-end family. The SFI offers very wide RF modulation bandwidth of up to 10 GHz. It covers the frequency range from 11 GHz to 21 GHz for IF tests and from 70 GHz to 175 GHz for tests in the sub-terahertz region in combination with the FE110ST and FE170ST front ends. In addition to the RF interface, the SFI 100A also has analog IQ outputs, ideal for wideband signal generation in the baseband. Let's have a closer look at the solution with the help of two experiments: direct IF measurements at 14 GHz and characterizing a D-band power amplifier module at 144 GHz. For direct IF measurements, I use a 4 GHz wide 802.11ay signal transmitted at 14 GHz. Using the graphics feature of the SFI 100A, I can see the power spectrum of the signal loaded in the app. The SFI is directly connected to the FSW signal and spectrum analyzer, and I use the 802.11ay personality to demodulate the signal. We see the spectrum as well as the clean 16-QAM constellation. The EVM of around -38 dB, or close to 1.3%, is excellent for such a wideband signal, attesting to the excellent modulated signal quality generated by the SFI 100A. This ensures that you can characterize the true performance of your device under test. Next, we characterize a D-band power amplifier module from Nokia Bell Labs. For this experiment, we connect the FE170ST to the SFI 100A to cover the frequency range from 110 GHz to 175 GHz. The SFI provides the IF signal for up conversion by the front end. After successful connection, the frequency range on the SFI changes to reflect that of the FE170ST. We also see the connected front end in the GUI. The SFI fully controls the connected front end through the front end dialog. It automatically compensates for fixtures such as cables, smart accessories, and other components on the signal path, ensuring calibrated measurements at a defined measurement plane. This eliminates uncertainty and time-consuming calibration routines when changing the waveform, level, or frequency. In this experiment, the SFI automatically compensates for the cable and connected smart accessories on the signal path. I use an 8 GHz wide 802.11ay signal and transmit at an RF of 144 GHz. Using the NRP 170 D-band thermal power sensor, we can see that the level at the DUT plane does indeed correspond to the level set on the SFI, even as we change the set output level. On the receiver side, I use the FSW in combination with the FE170SR front end to demodulate the signal. Here again, we see a clean constellation diagram and an EVM close to -31 dB or less than 3%, reflecting excellent modulated signal quality for such a wideband signal, even at 144 GHz. Finally, I use the K18 amplifier measurements personality to visualize important performance metrics of the power amplifier module under test, such as gain compression, AM/AM, and AM/PM. Based on this, we can fine-tune the performance with the help of different DPD models. The FSW can directly control the SFI over a LAN connection, reading reference waveforms, loading pre-distorted waveforms, and setting parameters such as the level. This makes it straightforward and convenient to characterize your power amplifier and apply different DPD models using only one instrument as the interface. In this video, I have demonstrated how the Rohde&Schwarz SFI 100A simplifies wideband signal generation for modulated measurements at IF and in the sub-terahertz region in combination with the FE110ST and FE170ST front ends. You can do more with the SFI 100A. Talk to a Rohde&Schwarz representative or visit our website for more information. Thanks for watching.